Forces change the speed, direction and shape of just about anything. Press Start to begin. Whenever you push or pull, you're using a force. But isn't it odd that forces are invisible? However, even though we can't see them, we can see their effects. Just click on this apple. There it goes. It falls because there's a force acting on it. Forces change speed and direction of movement. And the force involved here is gravity. Gravity pulls the apple down towards the earth. Forces can change the shape of an object too, quite drastically in this case. Now, suppose you wanted to measure force. How could you do that? This spring is a good place to start. Give it a pull. We measure force with a unit called a newton. The N at the end of the spring weighs 10 newtons. The more force you use, the more the spring stretches, so we can measure force this way by measuring the stretch. Let's go back to gravity. But what is gravity anyway? It's a force that exists between all objects and pulls them together, but you only see its effects with really massive objects, like planets. Why? Because gravitational force is stronger the more mass the objects have and the closer they are. Planets exert a strong gravitational force on objects near to them. Take a look at this astronaut. Like all objects, she has mass, and her mass never changes. Weight, on the other hand, does change, because weight is a force and it depends on gravity. The Moon is smaller than Earth, so it exerts a weaker gravitational force. Why don't you drag the astronaut to the Earth or Moon and see what happens to her weight? On the Moon, the 60-kilogram astronaut weighs a mere 100 newtons, about as much as a small dog weighs on Earth. Now try the other one. On Earth, our 60-kilogram astronaut has a weight of 600 newtons. Let's look at forces and movement now. The weight of this apple pulls it down, but the branch pulls it up. The forces are balanced and the apple stays still. It's exactly the same with the apple on this table. Its weight pulls down, but the table pushes up, so it's static. It definitely won't magically tunnel its way through the table or anything. How about this van? The forces are balanced here too. There's no force pushing forwards and no force pulling backwards, and we're not moving. Thrilling. But what happens when we deliberately unbalance the forces? Click the van to start it. Now there's a large force pushing it forwards and a small friction force pushing backwards. The forces aren't balanced anymore, and that's what starts the van moving. Unbalanced forces like this always cause changes in the way things move. Now watch what happens when we ease off the accelerator. We're back to balanced forces. The force forwards from the engine is equal to the friction and air resistance pushing backwards. So notice that when forces are balanced, it doesn't mean things don't move. Balanced forces mean no change in speed, so our van moves along at a steady pace. Until we hit the accelerator and unbalance the forces again. Now we're going to look at two ingenious ways we use forces. The first is pressure. Press the finger down on one of the pins. Good, the pin went right in. Now try the other pin. Ouch, that's got to hurt. So what's going on here? The round end of the pin has a large area, so the force from your finger spreads out, creating low pressure. The sharp tip concentrates the force into a very small area, which creates high pressure. And how do we measure pressure? That's right, newtons per square metre. Another way we can apply force is to use a pivot. We call these forces turning moments. To work out moments, you need to multiply the force by its distance from the pivot. We measure moments in Newton meters. That's force times distance. This seesaw is balanced because there are equal moments on each side. The large weight close to the pivot is balancing the smaller weight that's further out. Now try moving one of the boxes to change the moments. Thank you. A wonderful demonstration of unequal moments. Let's look at some more turning moments. This nut is screwed way too tight and won't turn. What would happen if you used a longer spanner? Click and drag to find out. That worked! So, did you get that? We increased the distance from the pivot so the same force gave us a bigger moment. The bigger moment allowed us to turn the nut. Ready for a refresh? Forces can change the speed, direction and shape of an object. Forces can push or pull. Forces are measured in newtons. Balancing forces. When forces are balanced, a stationary object stays still and a moving object moves at a constant speed. If forces are unbalanced, the object changes speed, direction or shape. Pressure is force divided by area and we measure it in newtons per square metre. Moments are force times distance from the pivot. They're measured in Newton metres. I hope you're ready because it's time for a test. Question 1. What is the weight of a 20 kilogram box on the Earth? A. 2 newtons. B. 20 newtons. C. 200 newtons. Question 2. The unit force is A. The neutral. B. The newton. C. The neutron. Question 3. What can we say about an object that is not moving? A. There are no forces acting on it. B. The forces acting on it are balanced. C. It must be very heavy. Question 4. What are the units of pressure? A. Newtons per square metre. B. Newton metres. C. Newton squared. Question 5. A force of 4 newtons acts on a lever 2 metres from the pivot. What is the moment? A. 8 newton metres. B. 6 newton metres. C. 2 newton metres. Question 6. One way to increase the turning force on a spanner is to A. Use a shorter spanner. B. Hold it closer to the pivot. C. Use a longer spanner. Smart as you like. Nice score.
Alright, well this is my favourite part of the challenge. I don't know about yours. This is a football, or a soccer ball, depending on where you're watching this, filled kind of all the way up with water, so it's got a bit more weight to it. And I'm going to throw it really hard at the side of your head.
Thanks, yeah, brilliant.
I reckon expose the teeth, and I want to see eyes wide open, just so you can get the full extent of skull movement. Ready?
Oh, God. Is that any good or not?
Yeah, it's pretty good.
It's like one of those Newton's cradle things. The ball just stops dead and then your head carries on at the same speed.
That's ridiculous.
Look at this. I reckon this should be your Facebook profile picture. That'd be wicked.
In this tutorial, we're going to look at a PhET simulation called Forces in Motion. And in particular, we're going to examine a tug-of-war situation and look at the forces involved and start getting used to some of the terminology that we're going to encounter in this unit. I think you'll find a lot of these answers are very intuitive, and you probably innately have a pretty good feel for what's going to happen as we set up the situations that we're going to describe shortly. Now, as far as the tutorial is concerned, you see you have a rope on either side with 4 knots. That represents 4 different positions for people to grab onto the rope and pull either to the right if they're on the right hand side or the left on the left hand side. You also see a series of men down below, small all the way up to large, representing small to large force capabilities. So let's start with a basic situation where we put 2 people of equal size on either side of the rope. And you see right away it labels. There's a force acting to the right, a medium-sized arrow represents that force, and a force acting to the left. These arrows are vector quantities. So the longer the arrow, the bigger the force. In fact, if I get rid of this little blue guy and put a big blue guy, you see the arrow gets larger because he's capable of a bigger force. Now let's take it back to our original situation and see what happens. So we're going to remove the big guy and put down the little guy. Now I assume most of you will be able to predict what's going to happen when I click go. If we have equal people on either side of the rope, both exerting the same force, when I click go, they both pull and nothing happens. We say in this situation the forces are balanced. The left force is exactly equal to the right force. Now because forces are vectors, I would also say that the right force is positive and the left force is negative, and when I add up those 2 forces, I get a sum of 0. So the sum of the forces is equal to 0, and in that case we see that the object does not move. Now let's pause again and let's add another guy on this side, a little guy. Now right away we see that the right force is now a little bit bigger, and of course now the sum of the forces is to the right, a tiny arrow to the right. We'll figure out how we get that value in a second. Now when I hit go, we see that the right hand side is winning and the cart starts to accelerate towards the right. We can even look at some values. If I click on this little box up on the upper right, we see that the right force adds up to 150 newtons and the left force is 100 newtons. Clearly if the right force is 150, then we can imagine that this big guy here is exerting 100 newtons of force just like this other guy on the left, and the little guy is adding an additional 50. So the sum of the forces is weighted towards the right, so our sum ends up becoming 50 newtons. 150 newtons minus 100. We call this value the net force. So in this case, we have a net force to the right, the object will accelerate to the right. So let's summarize so far. If you have an unbalanced force, meaning the sum of the forces is anything but 0, the object will accelerate in that direction. If the forces are balanced, then the object will not accelerate. And we've seen this scenario where we have people on either side that are equal and opposite, like what I'm showing you here. And the net force is 0, and when I hit go, nothing happens. But there is one more scenario that you have to be aware of. So I'm going to hit reset, and we're going to try something. Let's place this medium guy once again on the rope on the right. So right now we have an unbalanced force acting towards the right. It should accelerate to the right. And when I hit go, Lo and behold, it will. But now I'm going to add a guy to the left. Notice my sum of my forces immediately goes to 0, but the object keeps moving. So there's two scenarios. If the sum of the forces is 0, either A, it won't move at all, everything's balanced, or B, it will no longer accelerate. It'll just move to the right with a constant velocity. And you have to keep that in mind when you're doing dynamics. Now, again, we call the sum of the forces the net force.
What is friction? In cold season, you must have often rubbed your palms against each other to feel some warmth. You must have wondered how this heat is generated. This is because when we rub our palms together, an opposing force is produced on the surfaces of our palms, which then generates heat and we feel warm. This opposing force is known as friction. Let's discuss it a little more. A surface is never perfectly smooth. Even very smooth surfaces possess irregularities, which is visible only through a microscope. So when two bodies which are in contact with each other, the irregularities present on their surfaces tend to interlock with each other. Now, when we try to move one of the body on the surface of the other body, the interlocking of irregularities opposes the motion. This opposing force is called friction, and its magnitude depends on the degree of irregularities on the surfaces in contact, while its direction is always opposite to the direction of motion. Thus, friction is defined as the force which opposes the motion between any two or more surfaces in contact. Friction can be classified into two types: static friction and dynamic friction. Static friction: when a body is placed on a surface and it remains static or at rest on that surface, the friction it experiences is called static friction. Now, if we want to move such a body, we need to exert a force greater than the static friction. Dynamic friction: when a body is in motion on any surface, the friction it experiences is called dynamic friction. It is also known as kinetic friction, and its magnitude is always less than the static friction. Dynamic friction can be of three types: sliding friction, rolling friction, and pivot friction. Sliding friction is the friction experienced by a body when it slides over another body. For example, a block sliding on a surface. Rolling friction is the friction experienced by a body rolling on a surface. For example, a tennis ball rolling on the ground. Pivot friction is the friction experienced by a body due to its rotation about a pivot. For example, merry-go-round in parks. The related terms are